Hi, welcome to session 5 of the course Data Science for Engineers by the Department of AI and DS. So in the remaining sessions, we will be visiting some of the classical and important feature selection techniques that is used in the field of data science. We will not cover in depth, but we will see some of the classical techniques only. So what is feature selection? So feature selection, as the name suggests, it's selecting a subset of features from the total set of features. Or we can also define it as reducing the feature space by removing or throwing out some of the features. So the reasons for going for feature selections. Uh, so the first thing is we want to know which features are relevant. So like features like let's say ID of a person, Aadhaar ID or things like that, it will not help us in any way, shape or form to predict some variables, right? Because it's just a unique number. It doesn't has got any other meaning. So there may be some cases in which certain features are not at all relevant in our data science modeling. So that we need to find out. And surely one of the main reason is to maximize the accuracy of the model because there may be some features that are noisy which we have to remove. And it's always better to have a small model rather than having a very big model. That is, a model with a lot of features is less um, desired while defining a data science problem. And then the associated costs which, with for each of the features. So we need to minimize the cost that is required for setting up all these features. So there may be some features that are having least effect on the accuracy of the model, but may be expensive. So we try to optimize accuracy with the least expensive features. So these are some of the reasons why we go for feature selection. So we can generically say that there are three different methods for feature selection. The first one is filter method, where we rank features or feature subsets independent of the classifier model that we are going to use or the machine learning model that we are going to use. And the second one is called a wrapper method. It uses a classifier to assess features or feature subsets, and we iteratively delete or we take some variables. And the last one is embedded method, which is a combination of filter and wrapper method. And we will not be covering this in module 1. We will be just visiting the filter method and the wrapper method for feature selection. So to begin with, filter method. So the first method that comes under filter method is feature selection through entropy minimization or information gain. So entropy measures the uncertainty in the data. So the entropy value for a data, if the entropy value is high for a data, it means that there is a lot of uncertainty in the data. And it's hard to predict anything when there is a 50-50 chance, right? So we try to minimize the entropy so that uh, prediction is possible. Now the equation for entropy is given in the following, that is, it's denoted by a H, um, and it's equal to minus integral of, if you're talking about continuous features, then minus integral of x on p of x given wi and log of p of x given wi. So what we are doing is we are integrating on x, and it is p log p, and where p is p of x given wi, where wi is the class that is given. It's a conditional probability given wi, the probability that x would belong to wi, that is p of x given wi. So you can just think, if it is summation, you can just think minus sigma p log p. Okay, so this is one of the method in which we try to perform feature selection. We will remove features and we will see how the entropy is changing, and if we'll try to minimize entropy, and by using this concept we can select a subset of features. And the second method is correlation coefficient. So correlation between two features talks about their linear relationship. So they may be positively correlated or negatively correlated. If two variables are positively correlated, it means that when one variable is increasing, the other one also increases along with it. If it is negatively correlated, when one variable is increasing, the other one decreases. And the correlation coefficient that we are talking here is Pearson correlation coefficient, and this is the equation for that. Pearson correlation coefficient is equal to sigma of xi minus x bar into yi minus y bar, where x and y are the two features. X bar is the mean of x and y bar is the mean of y, and divided by square root of sigma xi minus x bar all square into sigma of yi minus y bar all square. The denominator parts handles the normalization, and this value Pearson's correlation coefficient, it ranges from -1 to +1. +1 means that both features are perfectly positively correlated. So if you take one vector 1 2 3 and the other vector multiple of 1 2 3, it can be multiple of 2, that is 1 2 3 becomes 2 4 6, or any other multiple, those are perfectly positively correlated, and so the value of Pearson correlation coefficient would be +1. And if it is negatively correlated, it becomes -1. If it is perfectly negatively correlated, it becomes -1. And the values that are near to 0 suggest that the features are very less correlated, and if it is 0, it means that they are not at all correlated. And the third set of the third way, the third set of ways to find out which features are important, and based on that we can remove the features. So that is by using chi-square test, and we would be seeing only one set of chi-square test in this module, that is goodness of fit. And if you want to completely see this area of chi-square testing, then there are other different methods also other than goodness of fit. There is independence of variables, and then there is homogeneity of proportions. So we would be seeing the goodness of fit test in the next module. In the next session. Thank you.